let's go ahead and jump into the material. First off, last week, what did we start doing? We started counting. And we started coming up with different ways to count. So let's say that there's 18 people in this room, and we decided to start a club with 18 people in this room. How many ways could we elect a president, a vice president, a secretary, and a treasurer, assuming we didn't have repeats? So we're electing 4 people, right? How many ways do we have to select our president?
18 to 4.
There's 18 people in the classroom. We're starting a club. How many ways can we pick someone to be the president? How many options are there?
18.
18 options. Holy cow. Okay. Now we got our president. Now, how many ways can we select our vice president, assuming it can't be the president?
17.
17. Okay. And now how many for our treasurer?
16.
16. And then how many for whatever the last one was I said? 15. Okay. And so the answer would be, we have 18 times 17 times 16 times 15, whatever that big product comes out to. On your test, do not write out some big massive number. Right? 18 times 17 times 16 times 15. That tells me exactly what your thinking was, exactly how you went through the process. If you write some big, humongous number, 1, 7, 6, 2, 9, 5, and it turns out to be the product of this, and you forgot to multiply that for some reason, there's no way for me to know that's what you were thinking. So don't just write some big number, otherwise I can't even give you partial credit. When you do something like this, 18 times 17 times 16 times 15, I can say, oh, that's what they were thinking. Now, because we do these products so frequently, keep multiplying by numbers as we decrement by 1, that's the same thing as 18 sub 4. That means 18 times 17 times 16 times 15. So that's without repeats. What if we had repeats? What if it was possible for me or whoever to be both the president, the vice president, the treasurer, and the secretary? Well, if one person can hold multiple positions. How many options do we have for our president?
18.
Still 18. For our vice president?
18.
Still 18. And 18. And 18. And what's 18 times 18 times 18 times 18? Do it in your head real quick, and it's 18 to the 4. All right, that's some fast math. So that counts with repeats. That counts without repeats. In general, here's your formula. N to the k is with repeats when there are n options and you're making k choices. Without repeats when there are n options and you're making k choices. Okay, now some notation you've probably come across before. Factorial. It's n really, really loud. N. N factorial has that exclamation point after it. What does n factorial mean? It simply means n sub n, where n is any natural number. So, what is 5 factorial equal to?
5.
It's just 5 times 4 times 3 times 2 times 1. Or in this case, let's see, 20 times 6, this one comes out to 120. Right?
Yeah.
That's 5 factorial. In general, we think about factorial as counting how many ways to arrange n objects in a list. If I were to arrange everyone in this class into some lineup, some list, some order, and assume that there's 18 of us in here, how many options do we have for who comes first? 18. Okay, now we got our first person. How many options do we have for who comes next? 17. And then 16. And then 15. ... All the way down to 1. And so the product of all those numbers, 18 times 17 times 16, etc., all the way down, is 18 factorial. That's how many ways we could arrange you all in a list. And so now you can count that. How many ways can we line all 18 of us up? 18 factorial ways. That's it. All right.
That's it. It's a massive number.
Now, how many ways can we arrange no people in a list?
No ways.
You boys, I'm going to split you up if you can't not talk. How many ways can we arrange no people in a list? So I got a list, and who comes first?
0.
Nobody. Okay, here's the end of our list. How many ways did we do it?
1.
1 way, not 0. Let me show you no lists. Now I'm going to show you one list. I'm going to show you no lists. Now one list. 2 very different things. So 0 factorial is equal to 1, not 0. You think about it as how many ways can you arrange 0 objects in a list? Make sense?
Yeah.
So that's the weirdest one. If you get that, you're pretty much okay. Now, sigma notation. Typically, students haven't seen it before. I don't know if you guys have. Is that scary or is that normal? Scary? All right. You say normal if it was normal, so I guess scary. Okay. So this is a capital sigma. That's what it's called, just a Greek letter. You start with what we call a dummy variable k here. Whatever your variable is here is what's going to be at the bottom. Now we say k equals 1, that means we're going to start with 1, and we're going to keep plugging in for k here, clear until we get to whatever n is, adding up all our results. So this is shorthand for writing 1 plus 2 plus 3, all the way up to plus n. That's a bit dense. Let's do a concrete example, and I think it'll make sense. So here we got the sum, here's how you read it, the sum of 2k plus 1 from k equals 2 to 7. Let's sum it up. So first thing we do is we plug 2 into this expression, 4k. What's 2 times 2?
4.
Plus 1?
5.
5. So when I plug 2 into that expression, it comes out to 5. Now I'm going to add what I get when I plug 3 into it. I'm going to do k equals 2, and then 3, 4, 5, 6, all the way up to 7. And that's when I stop. So plugging in 3, 2 times 3 is?
6.
Plus 1 is?
7.
7. Now when I plug in 4, what do I get?
8. 9.
9. Right? 2 times 4 is 8, plus 1 is 9. When I plug in 5, what do I get?
11.
When I plug in 6, what do I get?
13.
When I plug in 7, what do I get?
15.
When I plug in 8, what do I get?
17. Doesn't matter.
Bad question. You end at 7. So this tells you where you start, this tells you what you end, this is what you plug in for, and you're just adding up your results. And so whatever that sum evaluates to is whatever the sum evaluates to. Just plug it in. Okay, let's try another one. So we're going to do from k equals 1 to 6 of k squared. So what's my first number? 1 plus what's my next?
2. 4.
4, because you're plugging in 2 for k. 2 times 2 is 4. What's next?
9.
9, because you're plugging in 3 for k. 3 squared is 9. 16.
25.
25. Oh, sorry, that should be a plus. Plus what?
25.
Oh, 25 plus.
36.
And we're done. We end once we got to whatever that number was. Okay, what's the point of this expression? Imagine I wanted you to add up all the numbers from 1 to 1,000. All the evens from 1 to 1,000. How long would that take you to actually write out on your paper? Forever. It's ridiculous. But look at this. Let's look at the sum from k equals 1 to 500 of 2k. So plug in 1, what do I get?
2.
2 plus what's next?
4.
What's next?
6.
What's next?
8.
And if I keep going, what's my last number going to be?
1,000.
When I plug in 500, what do I get?
1,000.
1,000. So that's the reason that this notation is so absurdly useful. It helps you write really long sums very compactly. This is a way of writing the sum of all the even integers from 1 to 1,000. So it shows up once you get a bit further in math. If you go on and take college algebra, for example, I think they start introducing it there. The further you go in math, the more this notation needs to be used because we don't want to write out big sums.
Yeah.
So it helps you write out sums really quickly. Now, there's something very similar. The same way that that is called summation notation for writing out big sums, we have what we call product notation for writing out big products. It's the exact same thing, but it's just products rather than sums. And the only difference is, rather than using a capital sigma, you use a capital pi. So capital pi, this is, we're going to do the product of k from k equals 1 to n. This would be plug in 1 times, plug in 2 times, plug in 3 times, going all the way. So this is another way of writing n factorial. So let's once again do a concrete case. Oh, sorry, forgot my k here. So let's do the product from k equals 1 to 6 of k. What does that equal?
1 times 2 times
1, you plug in 1 for k, and then multiply by what you get next. Times 2, times 3, times 4, times 5, times 6. Which is, what is it, 720?
Yeah.
So in that case, it happens to be 720, but notice that that's also just the same thing as 6 factorial, is what we just wrote out there.
Yeah.
Make sense? All right, let's do this one really quick. Plug in 3, tell me the first thing to write.
8.
8. So 3 squared is 9, minus 1 is 8 times
15.
15. 3 squared is 9, or 4, when you plug in 4, 4 squared is 16, minus 1 is 15. Then we plug in 5, what do we get?
24.
24, good.
35.
And then we plug in 6, what do we get?
35.
35. Okay. So you might call that the product of your perfect squares minus 1 starting from 9 going up. Whatever. Not a very useful product, but a product in the way that we could write it. All right, let's write one more. I want you to do the product from k equals 1 to 0 of k here. What does that equal to?
That doesn't. You start at 0.
So you start at 1 and you go till you reach 0.
Well, then it doesn't matter because it's.
Yeah, how does that make any sense? You start at 1 and you go to 0. What's the answer there?
You wouldn't. It is 1.
The answer is 1. How on earth did he get that?
Oh, same thing as.
Because it's an empty product.
Yeah.
You're not multiplying any terms together. An empty product we call 1. Now, intuitively, students at first don't like calling empty products 1. They want to call it 0. If you're going to call it something, you should call it 0. Why do we call an empty product 1? Imagine I wrote some big list of numbers here. 17, 29, 36, whatever, 91. And we want to know the product of this big list of numbers, and I don't want to do it all myself. So I tell Bob, you do the first 4, Jack, you do the next 4, Bill, you do the next 4, and have you each multiply some of them together. And then I'll take all your answers and multiply them together to get the whole product. You with me? But what if Bob didn't get assigned any numbers? And so I multiply together everyone's product. Bob, he did no numbers. When I multiply his number in, what should I multiply by? 1, not 0. So an empty product is 1. An empty sum is 0. If we were doing the same exercise, and I said, let's sum up all the numbers, and I split it up into groups and gave each person some group to sum, and Bob didn't get assigned any numbers, when we added up his sum, we would do his was 0 because he wasn't given any numbers. So an empty sum is 0, your additive identity. An empty product is 1, your multiplicative identity. Make sense? Okay. So now let's jump into sets. Okay. Intuitively, what is a set? A set is simply an unordered, unique collection. In other words, it's a collection where order doesn't matter and repeating elements don't matter. It doesn't change the set. So unordered, we don't care about order. Unique, meaning we don't care about if you put the same thing in there 10 times. It doesn't change it. That's the intuition. Okay. Notation. How do we write out a set? We start with one of these curly braces, and then we write out some objects, and when we're done, we put our ending curly brace. All our objects are comma separated. So here's the set containing 1, 2, SpongeBob, and the set containing 2, 3. Question, how many things are in that set? 4? Yeah, 4 things. 1, 2, SpongeBob, and the set containing 2, 3. That's a single object in there. Good? How many objects are in this set? 3. Object, comma, object. 3 objects. A dot. Wait a second. Unique. Duplicates don't matter. This is the set containing 1, 2. There are only 2 things in that set. 1's in there and 2's in there. You can't find anything else in there. Repeats do not matter. Order does not matter in a set. Only 2 things in that set. Good? All right. Notation. When we want to say something is in a set, we use that little in symbol. Draw it a bit bigger. Looks like this, with a line that way. That's the in symbol or is a member of. So when I say X, that symbol A, this means A is a set and X is an element of that set. X shows up somewhere in the set. The elements of this set are 1, 2, SpongeBob, and the set 2, 3. Those are the 4 elements in that set. When I say X is in A, it means X is an element of set A. You instantly know when you see that notation that the thing on the right has to be a set. Make sense? Okay. So true or false? 1 symbol set containing 1, 2, and 3. Is this statement here true or false? True. It says 1 is in the set containing 1, 2, and 3. That's true. It shows up somewhere in there as one of its elements. Let's see this one. Is this one true or false?
False.
False?
Yeah.
1's right there. So 1 is in this set. correct?
No,
False.
second.
What are in this set? In this set, we have the set containing 1, and we have 2. 1 is not one of the elements in that set. The set containing 1 is an element of that set. 1 and the set containing 1 are two very different things, very different mathematical objects. A hat and a man wearing a hat are two very different things.
Yeah.
Just because the same symbol happens to show up here that shows up there doesn't magically make them equal. So 1 is not in the set containing 1 and 2. So that's how you would write that is not a member of. Next one, true or false?
True.
True. The set containing 1 is an element of the set containing 1 and 2. It is one of the things that we listed out in that set. It's one of the objects in there. That's all it means. Good?
Yep.
All right. Now, when do we say two sets are equal? We say sets A and B are equal, double if and only if, every element of A is an element of B, and every element of B is an element of A. If everything that's in set A is in set B, and everything that's in set B is in set A, we say the two sets are equal. Question: are these two sets equal?
Yeah.
Over here, I have the set 1, 3, 2, 2, 1, 1, and 3, 2, 1.
Yes.
Let's check if they're equal. Does everything that's in here show up in here?
Yeah.
Let's check. Is 1 in there? Yes. 3.
Yes.
Yes. 2. Yes. 2. Yes. 1. Yes. 1. Yes. Okay, so everything that's in here is in here. Now we check the other way. Is everything that's in here in here? 3. Yes. 2. Yes. 1. Yes. Now notice how many elements are in this set. 3. Because remember, this and this are identical. They're the exact same thing. There is no difference between them. And so however many things are in here are the number of things that are in here, which is 3. Repeats don't matter. Order doesn't matter. Feel like you're getting the intuition? Okay. Now, the size of a set, we call it cardinality. Cardinality, size, same thing. So the cardinality of a set, A, written, we use the absolute value symbols to talk about the size of a set. So that's not absolute value, it just means the size of a set, but it's the same symbols. So the cardinality of a set A, written like that, is the number of elements that show up in A. What's the cardinality of this set? 3. What's the cardinality of this set?
3.
What's the cardinality of this set?
2.
What's the cardinality of this set?
4.
4. Not 5. Good. Okay. We say a set is finite if and only if its cardinality, the size of it, its size is going to be some number, is in, I don't know, have you guys seen Fancy Z, Geometry Kids?
No.
Okay, that's just shorthand for the set of all integers. So, oh shoot, and I also did that over here, huh?
Well, that's okay.
Let's scribble really quick. So, fancy N here is shorthand for the set of all natural numbers. All the natural numbers are 0, 1, 2, 3, ... All your integers, which we represent with this fancy Z, is the set of -3, -2, -1, 0, 1, 2, 3, ... So it's all your positive and negative whole numbers, including 0. So you can think, in a sense, the naturals are half the integers.
Yeah.
Make sense? So that's all that fancy Z means, the integers. So, we say that a set is finite if and only if its size is an integer. A number like 7, 13, 21. Then we say it's finite. So what is the cardinality of this set? We're doing the cardinality of this set right here. This is a set containing square, triangle, the set 1, 2, and 17.
4.
4. Is 4 an integer?
Yes.
Then this is a finite set. It is not an infinite set. It's finite. There's a finite number of things in there. Now the naturals, remember, the naturals are the set 0, 1, 2, 3, 4, going on forever. How many naturals are there? The naturals keep going. 5, 6, 7, 8, 9, 10. Keep going forever. How many naturals are there? An infinite number. Is infinity an integer? No. So, if we're going to call something, may as well use the symbol infinity. It's as good as anything. But that is not an integer. So if the size of the set, the cardinality of the set is not an integer, we say it is an infinite set. It is not finite. It is infinite. Make sense? Okay. Set builder notation. Hopefully you've seen this before. But remind you in case you have, or in case you haven't. Set builder notation. We do starting a set, something that we call a dummy variable. It doesn't matter what that variable is. It could be x, y, z, whatever you want. A colon, followed by some predicate in terms of your dummy variable. So it's going to be some dummy variable. We always read the colon as such that. And then some predicate that the dummy variable, some predicate in terms of the dummy variable. Some condition. Remember, a predicate returns true or false, right? And so when you plug x into the predicate, if it returns true, that means x is in the set. And if it returns false, that means x is not in the set. So you do a dummy variable, colon, then some condition in terms of that dummy variable. This can be a bit, that's the first time, so let's just do some examples. I'll do the first one and then we'll have you guys do it from there. Let's say I want to write down the set of all evens. How on earth am I going to write down all the even numbers? It's an infinite set. I can't. So we need some notation to write down the set of all the even numbers. So I'm going to say that this is a set of all x such that if a number is even, what do we know about the number?
It's divisible by 2.
It's divisible by 2. 2 divides x. That sign there just means is divisible by, or 2 is a factor of x. You can think about it as 2 goes into x evenly is what that says. How would you tell your third grade sibling what an even number is?
You can divide by splitting.
Yeah, you can. 2 goes into it some number of times. So that's what this is saying. 2 divides x. And what else do we require? That's your and symbol. Don't forget your and symbol.
It is greater.
What does x have to be in order for it to be even?
Has to be an integer.
It also has to be an integer. So typically we want to say the integer part first. So we would say x is an integer and 2 divides x. Notice this is a predicate. It's something that's either true or false. If I plug in table for x, is table an integer? No, so it would return false. If I plug in 17, it returns true. Notice this is a predicate. Plug in x there. If I plug in 7, it returns false. 2 does not divide 7. 2 does not go into 7 evenly. If I plug in 8, it returns true. So it's a set of all x such that x is an integer and 2 divides x. That's what we mean by the set of all evens, and there we go writing it in set builder notation.
If 2 divides x, doesn't that kind of imply that x is already an integer?
You're kind of cheating by saying that without ensuring x is an integer.
Isn't it only defined on the integers?
Right.
Oh, so you have to, okay.
So that's why it would be more natural to list that first.
Right.
Okay. So now I did the evens. Let's see if you can come up with something for the odds. How would we write out all the odds here using set builder notation?
You would start with x.
We could use x, we could use whatever. Let's just switch it up some, just like you see the dummy variable doesn't matter. This time I'm going to use an n, I guess. So it's going to be a set of all n such that what?
Such that n is an integer.
N is an integer.
And 2 divides x minus 1.
It's kind of a weird way to say it. What did we say it means to be n?
That's kind of weird thing.
And n is equal to 2 times m plus 1,
Yeah.
where m is an integer.
Yeah.
That's what it means to be odd. Even is it's written as 2 times a number. Odd is it's written as 2 times a number plus 1. All right. Now, you're going to notice something over and over again. We start out saying it's all the x such that x is an integer and blah, blah, blah. All the n such that n is an integer and blah, blah, blah. Because that happens so often, when we write set builder notation, we often start by using it's all the x in the integers such that 2 divides x. So that we don't have to instantly write that condition saying it's coming from a particular set right out the door. And so we could have done the same thing here. It's all the n in the integers such that n equals 2 times n plus 1, where m is also an integer. Okay, perfect square. Let's write all the perfect squares. You know what the perfect squares are, right? So the perfect squares are, just writing some out for you, 1, 4, 9, 16, 25, 36, 49, etc. Keeps going. All the perfect squares. Oh, sorry, starting with 0. 0 squared, 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, etc. All the perfect squares. I want to write them now all as a set. I don't want to have to write out infinitely many things. It takes too long.
Right.
So let's write it as a set. What is a set of all perfect squares? How might we say that?
X in the integers such that x squared.
Such that x squared? I don't know what that means. I'm going to use a y. Kind of telling. It's a set of all y in the integers such that what? What does y have to be a perfect square?
Has to be equal to 2 numbers times 2.
Has to be a natural number. That could be a specification we put on y. Has to be what?
It has to be equal to a number times itself.
It has to be equal to a number times itself, where that number is a integer. So it's a set of all y and z where y is equal to x squared and x is an integer.
Okay.
So there's a way that we could write that.
Could you also write your x in integer at the beginning as well? So y in the integers and x in the integers.
Y is what we're calling the perfect square.
Okay.
So it has to be the product of your square cubed, or of your x squared.
Exactly.
Okay, so set builder notation, we use it to write out infinitely large sets. That's why it's so useful. Now, definition of subset. We say A is a subset of B, and we write it as A is a subset of B, provided every element of A is in B. If everything that shows up in set A is also in set B, then A is a subset of B. Make sense? True or false? The set containing 1, 2 is a subset of the set containing 1, 2, 3. Does everything that's in here show up in here?
Yeah.
Let's look at everything in here. We have 1. Does that show up in here? 2. Does that show up in here? Perfect. So this is a subset of that. Everything that's in this set is in this set. So this set is a subset of this set. The left-hand set is a subset of the right-hand set. Go ahead.
You mean to draw your subset symbol with a line under it?
Yes. So, trying it out big, we're saying A is a subset of B. A, it's like a sideways horseshoe with a line under it. B.
I thought that meant.
That means subset. You're thinking of proper subset. We're not going to worry about proper subset right now. Proper subset means that they can't be equal.
Right.
Subset allows for equality. Okay. So let's look at this one now. Is a set containing 1, 2 a subset of the set containing 1, 2, and 3? Is everything that's in this set in this set? Let's see.
Yeah.
What's in this set? Tell me something in this set.
1, 2.
Tell me just one thing in the set.
2 is in the set.
2's in the set. Is 2 in this set?
No, it's not.
No. What's in this set? The set containing 1, 2, and 3. This set over here only has 2 things in it. Namely, the set 1, 2, and 3. Neither of those are things in here. Now, what you're going to get confused by early on, the first time you come across this notation, is the difference between subset and is a member of.
Yeah.
This whole thing shows up somewhere in there. That's what this says. This is true. When I put the subset symbol in there, that means each of the individual things in here show up somewhere in here. And that is false. It is not a subset. Very easy to get confused by the difference between is a member of and is a subset of. We're talking about subsets. Good? Question. I tell you A is a set. Is A a subset of A?
Yes. A appears.
Does everything that shows up in A show up in A?
Yeah.
Yeah, they're the same set. So every set is always a subset of itself. Everything that shows up in a set always shows up in that set. I have no idea. Yep. Is he the only one?
Only one in our class.
Hope he's the only one. Okay. Special notation. I hate writing curly braces like this. Very annoying. And so we have a special symbol, a 0 with a line through it. This means the empty set. It's just shorthand for the set with nothing in it. So I don't have to keep writing those squigglies over and over again. Very annoying. Good?
Okay.
All right. Any questions before we move the camera? All right. So now, when you're working with sets, you're often trying to prove that two sets are secretly the same set. They're somehow the same. In geometry, you're going to be looking at your sets, or your lines, sometimes you're going to view them as sets of points. Sets of points satisfying some condition. And so you're going to want to prove that this line is somehow the same as this line over here. And the way that you're going to prove that is you're going to show every point on the first line is on the second line, and every point on the second line is on the first line. And therefore, the two lines are actually the same line. That will be in geometry, but in general, when you're trying to prove two sets are equal, you need to show everything that shows up in one set shows up in the other, and everything that shows up in the other shows up in the one. So I'm going to do an example of a proof showing you two sets are actually the same set. So let's go through an example. So we have our set here, E. E, what is E? Tell me, like I'm a toddler, what E is. Look at that. Don't just scream it out. Think about it for a second. See if you can read that.
Is it even numbers?
Don't scream it out. Just think about it for a second. E, what is that? So E is equal to the set of all x in the integers such that 2 divides x. So it's all the integers divisible by 2. What are all the integers divisible by 2? The evens. So here's a shorthand way of writing the even. Same thing we have written there. Okay. So E is the set of all evens. And F here, a bit more convoluted. It's a set of all integers z, such that z is equal to a plus b, where a and b are odd. So z is every possible number you can write as a sum of two odds. In other words, let's see, is 6 going to be in this set F?
Yeah.
How do you know 6 is in that set F? Because I can write it as 3 plus 3, where it's two odds.
Yeah.
Does 19 show up in the set F here?
No.
No, because you cannot pick two odds that add up to 19. If you were to say it's 9 plus, now you have to use 10, which is not odd. If you were to try to write it as 7 plus something, you'd have to use 12, which is not odd. And so 19 you cannot write as a sum of two odd numbers. 6 you can. So is it true that all the numbers you can write as a sum of two odd numbers is the exact same thing as the evens?
Yes.
That's what we're going to prove. Make sense? Okay. What does it mean for two sets to be equal?
Uh-huh.
It means everything that shows up in the first set shows up in the second,
Okay.
and then everything that shows up in the second shows up in the first. So it's kind of like doing two proofs in one. First, I need to show everything that's in E is also in F, and then I need to show everything that's in F is also in E. If I wanted to know two classes were composed of the same students, how would I check that? If I wanted to know all the same people who were in geometry were also in biology, how would I check that? I need to make sure everyone that's in geometry is also in biology, and then I need to check that everyone that's in biology is also in geometry. You'd have to check it both ways in order for those classes to actually be the exact same kids. Make sense? So that's exactly what we're going to do here. So I'm going to go this direction first, draw my arrow here. It's kind of like doing an if and only if proof. And I'm going to show that everything that's in E is in F. So I'm going to start out with, give me anything you want out of E. I'm going to prove to you it's also in F. Doesn't matter what you give me.
A.
So I'm going to use an N, but just because I'm going to use my A and B when we get to this part. So let N here be anything in E. You could have picked anything you want. I don't care. I'm going to show you it's also in F. Now, since m was in E, what's the one thing I know about n?
It's divisible by 2.
It's even. Because that's what E is. It's all the evens. If I say, here's a secret even number, what do you know about it?
It's even.
It's even. That's what you know about it. Or it's divisible by 2. So 3. Then, there exists some integer m. There exists m in the integers such that n is equal to 2m. That's what it means to be even. You're equal to 2 times an integer. What does it mean to be even? It means 2 goes into you some even number of times, which we're calling m. How do I know that 18 is even?
2 goes into it.
2 goes into it. How many times does 2 go into it?
9 times.
9 times. Since 2 goes into it 9 times, then it's even. If n is even, then 2 must go into it some number m times. So that 2 times m gives you your number. Because 2 goes into it m times. Overstating it? Okay. Now how do I write, what am I trying to prove? I'm trying to prove n is in F.
Yeah.
What is F?
Even.
It's all the numbers that can be written as an odd plus an odd.
Yeah.
So I need to prove that this can be written as an odd plus an odd. So how can I write that as an odd plus an odd? What does it mean to be odd?
2 times the number plus 1.
2 times the number plus 1. So I can write this as 2m plus 1. So far we cheated.
Right. Minus 1.
Plus negative 1. Is negative 1 odd?
Yes.
Yeah.
Yeah.
Is 2m plus 1 odd?
Yeah.
Yeah, if 2m's even, adding 1 gets you now to your odd. So n is equal to an odd plus an odd.
Yeah. Okay.
That's what f is. It's a set of all integers that can be written as odd plus an odd. So 5. Therefore, n is in F. Let's go through very concretely what this says. It gave me a procedure for showing how any even you give me is also in F. So give me a concrete even number now. Pick any even you want.
16.
What?
8.
8. So 8 is our n here. Now since 8 is even, it can be written as 2 times 4. So in that case, n would have been 4. And now I say, notice that you can also write 8 as equal to 2 times 4 plus 1 plus negative 1. What's 2 times 4 plus 1? 9. Is 9 odd?
Yep.
Is negative 1 odd?
Yep.
So 8 can be expressed as an odd plus an odd. This gave you a procedure for showing how any n you want is always an odd plus an odd. Pick any even you want. 6. So n would have been 6. What would m have been here?
3.
3. And so 6 would have been equal to 2 times 3 plus 1. Sorry, that's why I hate those. 2 times 3 plus 1 plus negative 1. And so there we go. I showed you how it can be written as
On the opposite.
an odd plus an odd. So this procedure works for any even you choose. You can pick 27 trillion and it doesn't change the way the procedure works. So I gave you a procedure now that works for any even number you choose. You see how that works?
Now we need to go the other way.
Right, so now I need to go the other way. Now I need to show, pick anything you want out of here, and I can prove to you it's even.
Yeah.
Okay, so now we're going the other way. Now we're going this way. That's an arrow pointing to the left, sorry. My handwriting gets sloppier as the class goes on. How do we start this? I need to show everything that's in F is in E. So I need to pick some random thing out of F and show it's also in E now. So this time, let n be some random thing in F. Then what do I know about n?
It's equal to a plus b.
Then it can be written as a plus b, where, what do I know about a plus b?
Or odd.
They're odd, where a plus b are odd. Okay, what does it mean for A to be odd?
It's equal to 2.
It's 2 times an integer plus 1. What does it mean for B to be odd?
2 times an integer.
It's 2 times an integer plus 1. So then I can say, then there exists 2 integers. I'll call them x and y. There exists x, y in the integers such that A is equal to 2x plus 1 and B is equal to 2y plus 1. That's what it means for A and B to be odd. Now, let's look at what their sum is. Then A plus B equals what? What did A equal? 2x plus 1. What did B equal? 2y plus 1.
2x plus 2y.
Add all that up, we get 2x plus 2y plus 2. Factor out the 2. I know you guys are terrified of factoring. That's 2 times x plus y plus 1. And so A plus B is equal to 2 times an integer. 2 times something is always even.
Yeah.
Take an integer, add 1, you're left with an integer. Multiply it by 2, you're always left with an even number. Pick any integer you want, 17. Multiply it by 2. You got an even, namely 34. Pick 5. Multiply it by 2, you got 10. An even number. Any integer here, doesn't matter what this is, once you multiply it by 2, you're back to even. So A plus B is equal to that. 10. Therefore, n, which was equal to A plus B, is even. Therefore, really running out of space there. Therefore, n is in F. And there we have it. So I proved everything in E was in F. Oh, sorry, in E. I proved pick something in E, it's also in F, or it's also in F. Now I said pick something in F, it's also in E. And so the sets are equal to each other. So that's how you prove set equality. Pick something from the first set, prove it's always in the second set. Pick something from the second set, show it's always in the first set. And you're giving out some procedure for how you can always do this. So now let's go through our procedure here in the case of a concrete number. So let's pick n to be something out of F. Give me a concrete number, whatever.
18, 15.
Well, it's going to have to be even because we're going to prove that it turns out it's going to be even. So
18, 15.
18. So 18 can be written as the sum of two odds. So 18 is our n here. What's our a and our b going to be here? Give me any two odd numbers that add to 18.
15 and 3.
15 and 3. So there's our a and our b. Since 15 is odd, 15 can be written as 2 times something, what? 7 plus 1. And 3 can be written as 2 times something, what is it? 1 plus 1. So there's our a and our b. Our x is 7 and our y is 1. And so we said, notice that a plus b, right here, a plus b is the same thing as 2x plus 1 plus 2y plus 1. Or in our concrete case, 2 times 7 plus 1 plus 2 times 1 plus 1. Which is the same thing as when we add our two 1s together, it's going to be 2 times 7 plus 2 times 1 plus 2. Then we factored the 2 out of all of it, and we got 2 times 7 plus 1 plus 1, which is even. So that's following the exact procedure, plugging in some number. And now 18 here doesn't matter what you pick. As long as you pick it as something that can be expressed as a sum of two odds. In other words, picking two odds here you want, this will always work. Following the same procedure. So that's what you're doing in these proofs, is listing out these procedures. Okay, let's do a really small proof. The two things that are going to confuse you a lot. We're going to prove that if x is in A, then the subset, then the set containing x is a subset of A. And that's if and only if. If x shows up in A, then the set containing just x is a subset of A. What does it mean for this to be a subset of that set? It means everything that shows up in here is in there.
Yeah.
What's everything that shows up in this set?
X.
X. So everything that shows up in here, X, has to be in A if the second-taning X is a subset of A. So saying X is in A is the exact same thing as saying the second-taning X is a subset of A. They'll say logically equivalent things. If this is true, then this is true, and vice versa. Make sense? Now that's what we're going to prove. So let's assume X is in A. So we're going this direction. Assume you're antecedent. Show that implies your conclusion. Assume X is assume X is in A. Then every element of the second-taning X is in A. Because X is in A. There, so the second-taning X is a subset of A. We showed everything in there was in there. Very simple, straightforward proof. Could have all been done one line, but I want to split it out piece by piece. Now let's go the other direction. Let's show that this is true, this is true. So assume your antecedent, show that implies your conclusion. So now let's assume the second-taning X is a subset of A. What does it mean to say the second-taning X is a subset of A? It means everything that shows up in this set is in A. So then every element of this set is in A. Is X an element of this set? Yeah, it's the only element of the set. So X is in A. And we're done. All right, let's do a somewhat more interesting proof. First, we need a definition, though. So a list of three integers, A, B, and C, is called a Pythagorean triple, provided a squared plus b squared equals c squared. So just a definition, just a name for certain types of three-element lists. So let's look at this list. Tell me, is this a Pythagorean triple?
Yes.
3, 4, 5. How would you check that? What's 3 squared?
9.
What's 4 squared?
16.
9 plus 16 is?
25.
Is that 5 squared?
Yes.
Yes, so in this case it works. That squared plus that squared equals that squared. Let's try another one. 5, 12, and 13. What's 5 squared? 25. What's 12 squared? 144. What's 13 squared?
169.
169. Is 25 plus 144 169? Yes. So once again, that's a Pythagorean triple. Let's try this list. 1, 2, 3. Is this a Pythagorean triple? How would you check it? What's 1 squared?
1.
What's 2 squared? So we have 1 plus 4 equals, what's 3 squared? 9. Is that true? 1 plus 4 equals 9? No. So the majority of the time that you write three numbers in a list, it is not going to be a Pythagorean triple. There are very special numbers that happen to do that. With me so far?
Yeah.
Okay. Now before we do our proof involving this, once again, since you guys always struggle with factoring, let's remind ourselves of some of our basics. What is a plus b squared equal to?
B plus b squared.
Now, can I just write this? Or is there someone who's saying, how did you get that? Is there anyone here who you see that and you say, how? Are y'all just lying to me? Okay, someone's thinking how. You're just not going to say it. All right, a plus b squared. What does that mean? It means a plus b times a plus b. That's exactly what it means. To square something. Now you got to distribute to each element. So I got to do this multiplied by that, this multiplied by that, and then b multiplied by that, b multiplied by that. So what's a times a? A squared. What's a times b?
B squared.
What's a times b? A times b. Okay, so we did a to both of them. Now we got to do b to a. What's that? B times a, or a times b, same thing. And now we got to do b to b. What's that? B squared. So we get a squared plus, how many ab's do we have? 2 ab's plus b squared. Okay, doing the exact same exercise when it's minus sign there, you would get a squared minus 2ab plus b squared. Well, that's going to be plus b squared because negative b times negative b is positive b squared. Okay, reminding you where those came from. So with that, let's go over a more interesting proof. Let's see. Am I going to get both columns? Ooh, can I get the whole board? Yes. All right. So, if P is equal to the set of all three element lists, A, B, C, such that A, B, and C are all integers, and A squared plus B squared equals C squared. So what is P the set of? Pythagorean triples. It's a set of all the things like this. Not including that one. Right? Okay. So, let P be the set of all Pythagorean triples, and let T be the set of all P, Q, and R, where P can be expressed as x squared minus y squared, Q can be expressed as 2 times x times y, and R can be expressed as x squared plus y squared, where x and y are any two integers. Then T is a subset of P. Or in other words, what we're going to prove is that if I were to ask you to come up with a bunch of Pythagorean triples here, I'm going to come up with numbers that satisfy it. You would just pick any two x and y's you want, and then you would calculate your three numbers this way, and it would give you a Pythagorean triple. That's what we're going to prove. So let's try this out really quick. Give me any two x and y you want.
5, 7.
So we'll say x is equal to 5, and we'll say y is equal to 7. Any of you have a calculator? If someone has a calculator, pull it out real quick, just in case you need to do quick arithmetic. So now, what is our p going to be equal to? Oh, let's make sure our x is bigger than our y so that we're not dealing with negatives. It still works with negatives, but just don't want to have negatives. So, what is x squared? What is y squared? What's 49 minus 25? 24. So we're saying our first thing is 24. What's our second thing? What's 2 times 7 times 5?
770.
Right? And now, what is 49 plus 25?
747.
Right. So now, the question is, here's a check. Do this squared plus that squared, and see if it's equal to that squared. Let's see if this actually worked. It's the same. So we just came up with the Pythagorean triple. Pick any x and y you want. This will always work. It'll give you a Pythagorean triple. That's what we're proving.
Is there any intuition for why that's the case?
Now, well, yes. With the complex numbers and looking at it as a rotation in the complex plane. It's really not even that hard though. So, unfortunately, we won't be doing it. Okay, so let's go ahead and get started with this proof. So I'm going to prove that all the t's that we generate this way here are in fact p's, Pythagorean triples. Or in other words, t is a subset of p is what we're proving. So let p and t be set as given above right there, and pick some random thing out of t. I need to prove that that random thing is also in p. So p, q, and r are in t. All we know about p, q, and r is that they were generated this way for some two integers, x and y, we don't know what they were. So here's our random element in t. I need to show that this thing is also in p. Now since p, q, and r, this list was in t, then that means that there has to exist integers x and y, such that p is equal to x squared minus y squared, q is equal to 2xy, and r is equal to x squared plus y squared. Right?
Yeah.
Now what does it mean to be a Pythagorean triple? What did it mean to be one of these numbers?
Means that
It means that squared plus that squared equals that squared. So this is only a Pythagorean triple if that squared plus that squared equals that squared.
so where's you at?
So let's check if that squared plus that squared equals that squared. So what is p squared plus q squared equal to? Well, what's p? So p is x squared minus y squared. And we're doing that squared plus q squared, which is 2xy squared. Now, make sure you're still got your algebra here. So when I do this whole thing squared, it's a difference. It's the exact same as what we did right here.
Yep.
But now instead of a, we have x squared, and instead of b, we have y squared. So it's going to be that thing squared. What's x squared squared?
X to the 4.
X to the 4. minus 2, the first thing times the second thing. Oh, thank you. Minus 2, the first thing times the second thing, or in other words, x squared, y squared, plus this thing squared, which is y to the 4. Good. Plus, now hopefully you know how to square this thing. What's 2 times 2? What's x times x? What's y times y? Y squared. Okay, and notice what we got here. This is equal to x to the 4. We have negative 2 x squared y squareds and positive 4 x squared y squareds. How many x squared y squareds do we have? Just 2. So we have positive 2 x squared y squareds. And then finally, plus y to the 4. Now, super crazy factoring that you guys all know and love. This is the exact same thing as x squared plus y squared squared. Just go in the reverse direction. Notice that's like what we have right here. This is the same thing as that. Just like this is the same thing as that. So this thing squared is right there. 2 of that times that is right here. And then this thing squared is right there. So we're just going from here to here. And notice that, what is our definition of r? R squared. So I guess we could add one more line, therefore, whatever we're on for. Therefore, this ordered triple, PQR, is in P. So there we go. We proved that that formula always works for generating a Pythagorean triple. Alright. So that was our hardest part, dealing with sets. Now, back to a slightly easier thing, counting subsets. How do we count the number of subsets you can get of a particular set? So I give you the set 1, 2. How many ways can we make a subset of 1, 2? Let's say I've got 2 people in the classroom, person 1 and person 2. How many ways can I take a subcollection of those people?
4.
There's 4. I could choose none of them. I could choose Tom. I could choose Bill. Or I could choose Tom and Bill.
Yeah.
Those are all the possible 4 subsets I can make of that set. Make sense? What if we had 3 elements? Tell me all the subsets now I could make of a 3-element set containing 1, 2, and 3.
The empty set.
First off, well, maybe we should have started with 1. Let's say I have a 1-element set. How many subsets can I make of a 1-element set? 2. I can make the empty set, and I can make the set containing 1. Right? And when it was a 2-element set, we could do 4.
Yeah.
If it's a 3-element set, how many are there going to be? 6? Let's try it. So, let's write out all our subsets. I can have the empty set, get none of them. I can have just 1,
Just 2.
just 2,
Just 3.
just 3.
1, 2.
I can have 1, 2.
2, 3.
I'll do 1, 3 first. I could have 2, 3.
And then 1, 2, 3.
And then finally, I could have 1, 2, 3. Sorry. How many do we have there? Count them up, you're going to get 8. Okay. Now, what if I said, let's do a 4-element list, or a 4-element set? 1, 2, 3, 4. How many could I make? Let's not write them all out again. Notice that everything I can make here, all these are already subsets.
Oh, yeah.
Right? If I were to write out all the possible subsets of this, it would include all these. That is a subset of that, that's a subset of that, that's a subset of that. All these are going to be subsets of that. Already. And so now I could just rewrite out all these again, but this time include the 4. So rather than the empty set, what's the empty set and the second, if I also include the 4 in that set, what do I get? The set containing 4. That one would be 1, 4. That one would be 2, 4. Dot, dot, dot. And the last one would be 1, 2, 3, 4. So if you think about it as we had 8 that didn't have a 4 in them, and 8 that did have a 4 in them, for a total of 16. What if I now decide to do 1, 2, 3, 4, 5? How many? I'm going to have 16 without the 5, and then 16 with the 5 for 32.
So it's just 2 to the.
So it's just 2 to however many elements you have.
2 to the k.
Right, so for our 4 element set, it was 2 to the 4. For our 3 element set, it was 2 to the 3. For our 2 element set, it was 2 to the 2. For our 1 element set, it was 2 to the 1. For our 0 element set, how many subsets can I make of the empty set? 1, the empty set. Or in other words, 2 to 0, which is 1. Don't forget, 2 to 0 is 1. So that's how you do it in general. You with me? So now we're going to prove that this is how you do it in general. And here's the way that we're going to count how many subsets you can make of a set. So let's think about it as picking people in this class to go on some field trip. We'll pretend that there's only 5 of you, so I don't have to write a bunch of stuff. There's Bob, Jane, pick another initial, V, Vanessa, I guess. Al, Caleb. All right, there we go. There's all 5 of you. Now, picking who I'm going to take on some field trip is the same thing as making a subset of that set. I can take everyone, I can take no one. Whatever choice I make is going to be a subset here. Now, for each one of these, they correspond with a list as to whether or not I should include that person, yes or no. So I have Bob here, and I decide, do I want to include Bob, yes or no? And I might say, yes, Bob, no to Jack, yes to Vanessa, no to Al, no to Caleb. So this list of Y's and N's corresponds to a particular subset. What subset is this?
B and B.
I chose B and I chose
V.
V.
Right.
So for every selection of people here, every subset I choose to make corresponds to one of these 5 element lists. So for each person, each element, I have a choice, yes or no, do I want to include them? So, got Bob here. How many choices are there as to whether or not I include Bob?
2.
There's 2. Either I include him or I don't. So there's 2 choices, 2 ways I can choose this person, 2 ways I can do that one, 2 ways I can do that one, 2 ways I can do that one, and 2 ways I can do that one. Either yes or no. So for each subset, there's 2 times however many elements in there, ways you can create a subset. That make sense?
No.
Now the counting proof for it. It's going to use this exact same logic here. So here's the counting proof. If A is a set such that the size of A is n, so there's n elements in there, then A has 2 to the n subsets. That's what we're proving. With me so far? So let A be any finite set, and let n be the size of that set. This doesn't make sense for infinite sets. We're not going to say an infinite set has 2 to the infinity subsets. Nonsense notation. Only makes sense for finite subsets. Good? So far? What do we know about A? It's a finite set with how many elements in it? N, whatever n is. That's how many elements it has. Okay. Now, what are the elements in A? We don't know. It could have been Bob, Jack, Vanessa, Al, and Caleb. It could have been the numbers 1, 2, 3, 4, and 5. All we know is it has n elements in there. I have no clue what the elements are. You with me? Yep. So then I'm just going to relabel the elements of A, A1, A2, A3, A4, dot, 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 AN. Just so I can talk about the things in there. I'm not changing what they are. I'm just calling them whatever I want. You can call something whatever you want. You have a choice of what names you use.
Yeah.
So I'm just relabeling them. Good so far? Okay, so now the next step. For every subset of A, we are going to create an n element list, just like this. We're going to create an n element list where Y is in the kth position if A sub k is in the subset. Otherwise, place an n in the kth position. So, we've got our list here, rather than Bob, Jack, Vanessa, whatever. we said relabel them. A1, A2, A3, A4, and A5 in this case, n happens to be 5. Now we're saying, for any particular subset you want to create, pick a subset of this.
A1, A2.
A1, A2. So in creating that particular subset, we include a y in the first position if A1 shows up there. We include a y in the second position if A2 shows up there. We include a y in the third position if A3 shows up there. In this case, it doesn't. And n, and n. So in the kth position, we put a y if and only if a sub k is there. So in the first position, we check for an a sub 1. In the second position, we check for an a sub 2. In the third position, we check for an a sub 3. In the kth position, we check for an a sub k. Okay, here just being some generic position there. Good? And now, observe that each n-element list of y's and n's corresponds to a single subset of A. Observe that there are 2 to the n such lists. You're making an n-element list with 2 options. How many ways can you make an n-element list with 2 options? 2 to the n. Right?
Yeah, that's right there.
So n, going back to what we started with, is your number of options. 2 is the size of your, or k is the size of your list. So in that case, 2 to the n. 2 times 2 times 2, n times. Did I say that right? Yes, I said that right. Okay. 2 to the n such list, therefore there are 2 to the n subsets of A. Okay, there's the end of that. Power set. Definition. The power set of a set A, written fancy P, A, is the set of all possible subsets of A. So take all its subsets and stick them together in one set. That's what the power set means. So what is the power set of the set 1, 2, and 3? We take all the subsets of 1, 2, 3 and put them together in a set. So a possible subset of the set 1, 2, 3 is the empty set. Here's a subset of that. The set containing 1 is a subset of that. The set containing 2 is a subset of that. How many subsets of the set containing 1, 2, 3 are there? 8. We wrote them all out, didn't we? Oh, and then we erased them. Right?
Yeah.
And here are all 8 of them written out once again. So take all its possible subsets, put them together in a set. That's what we mean by the power set. Now, terrible, terrible, terrible notation I'll never use. But the power set of A can also be written as 2 to the A.
What? Really?
Yes. This makes more sense when you know the set theoretical definition of numbers. But, doesn't matter. We'll avoid that notation. But yes, technically, the power set of the set 1, 2, 3 is the same thing as 2 to the 1, 2, 3 as a set. I will avoid that notation. But just so you see it, because it might show up in your textbook a couple times, that's what it means. So the cardinality of the power set of A is 2 to the cardinality of A. A here being the set 1, 2, 3, how many elements are in A? 3. How many subsets did it have? 2 to the 3, or 8. So the size of the power set of A is 2 to the size of A, which is also the size of the power set of A. Another way we could write it, but I will avoid this notation, and I will avoid this notation.
Are we gonna
But your book might use it a couple times.
Are we proving that?
No, it's identical notation. There's nothing to prove.
No, I mean, are we proving that?
We just did, because it's all the number of subsets you can make. And we proved for any set A, it has 2 to the A, 2 to the cardinality of A possible subsets.
Okay. Alright.
So that's what we just finished. Okay, and there we go. We're done with all the hard stuff. Last section, nice and easy. You've already seen everything in this section. It's just quantifiers. I force you to get comfortable with quantifiers early because I can't avoid using them. So, last section, quantifiers. We have 2 quantifiers. Our first one is the existential quantifier, backwards E. We read that as there exists or some. What does this say right here? There exists n in the naturals such that n is odd. Let's do that proof really quick. Observe, 1 is in the naturals, and 1 can be written as 2 times an integer plus 1. Therefore, 1 is a natural and 1 is odd. Okay, I proved there is an odd natural number, namely 1. Could have also proved 17 is an odd natural number. I could have also proved 31. Infinite number of ways we could have done that. Next quantifier, our universal quantifier. Just this upside down A. What does that mean? For all, for each, for every. However you want to read it. What does this line say right here?
For all x.
Natural numbers, x is greater than 0.
Yeah, for all x in the natural numbers, x is greater than or equal to 0. Or in other words, it says every natural number is greater than or equal to 0. For all x in the naturals, x is greater than or equal to 0. Okay. One more proof here. Let A be the set of all x in the natural numbers such that 6 divides x. With me so far? So A is just all the multiples of 6. 0, 6, 12, 18, 24, 30, etc. It's all the natural numbers that are a multiple of 6. I'm going to prove, then, for all x in A, x is even. If you take all the multiples of 6, they all happen to also be multiples of 2. Nice straightforward proof. Let's go ahead and prove it. 1. Let n be anything in A. What do I know about n then? If n was in A, and A is all the multiples of 6, then n is a multiple of 6. Am I losing some of you? What is A? It is a set of all x in n, all natural numbers, such that 6 divides x. Or in other words, 6 is a factor of x. Or in other words, 6 goes into x evenly. That's it. So let n be in A. What do I know about n? It's a multiple of 6. So then n can be written as 6 times something. We'll call it k, where k is just some integer. If n is a multiple of 6, it has to be expressed as 6 times some integer. All right, 3. Then n is equal to, finish it out for me.
2 times 3 times k.
2 times, we'll put the 3 times k in parentheses here. Didn't change anything, just split the 6 into a 2 times something. Is even. How do you know it's even? It's 2 times an integer. That's what it means to be even. Okay. Do some of our same examples that we did with quantifiers earlier in the class. Go through them again. Try and just help you get comfortable reading quantifiers. That's the only point here. And using now our in notation. So just reading now exactly what this says. This says for all x in the integers, and for all y in the integers, x plus y equals 0. Now is that true or false? False. Next one. Help me read it here.
For all x in
in
integers.
there exists a y in integers
Such that, remember, always read your such that after your existential.
x plus y equals 0.
Perfect. And so is that true or false?
True.
That one's true. All right, let's try reading the next one. You read it for me.
There exists x.
There exists x in integers
Such that, for all
y
In an integer.
in the integers,
Such that x plus
we don't say the such that, only after the existential. So there exists x in the integers, such that, for all y in the integers, x plus y equals 0. Now is that one true or false? There exists an x in the integers, such that for all y, x plus y equals 0. Does there exist some magic x such that no matter what you add to it, you get 0? So no. So in that case, it's false. And then finally, there exists an x in the integers When you say your next, there exists, you don't bother saying such that in the parentheses. So there exists x in the integers, and there exists y in the integers, such that x plus y equals 0. And in that case, it's true. Now, when we have repeating quantifiers like this, I said for all x in the integers and for all y in the integers, we don't like repeating like that if we can avoid it. So when it's for all x in a set and for all y in that same set, we instead write it like this. For all x and y in A. And so this one could have instead been written as, to save us a little bit of writing, it could have been written as for all x and y in the integers. Then that. Similarly for the there exists down here. We could have instead written this one as there exists x and y in the integers such that x plus y equals 0. Make sense? So now, reading those, a little bit more dense notation, getting you comfortable with the notation. We already went over the negation thing, but we can go ahead and go over it again. Negating alls and sums statements. How do we do that? So I have all swans are white, and I want to negate it. The procedural way that we do that. Let me rewrite this now using our notation. For all x in the swans, x is white. You see how this and this say the exact same thing? Now here's our procedure, our two rules. If you want to say not for all x in some set, some predicate about x, if I want to distribute the not, I bring it to the inside and switch the for all with the there exists. So in this case, if I want to now negate this, that's the same thing as saying there exists x in the swans such that x is not white. So if I want to negate for all x, if I want to negate all swans are white, or for all x in the swans, x is white, the way I would negate that is, negate it, just bring that to the inside, switch that one to not, and switch your for all with the there exists. So if I'm saying not all swans are white, what am I saying? I'm saying there exists a swan that is not white. There exists x in the swans such that x is not white. And so that's how you systematically negate these things. So if you want to negate a for all, you bring the negation inside and you switch the for all with the there exists. Similarly, if you want to negate a there exists, you bring the not on the inside and switch it to a for all. Good? All right. With that, we'll go ahead, do break, come back, and we'll grade homework and tests. Geometry kids, make sure all your homework